So in general, these greedy algorithms are really easy to understand and code and are fast, but um, do they work? For most optimization problems, they don't work. And for a few, they do work. And the proof is as to whether or not they work is subtle. All right, so and the way I'm proving this for the last few decades is, and I know other people do too, is using loop invariants. But I did redo these slides to emphasize the loop invariant part less and to put more emphasis on this game. But let's first talk about the loop invariant. The natural loop invariant is that the algorithm's solution so far, so far what the algorithm has done is optimal, right? We jump into the middle of the computation. The algorithm is committed to making decisions about some of the objects, and we say, so far what the algorithm has done is optimal. Well, this has no meaning because the algorithm has only made choices about some of the objects. Maybe it's chosen the line, or maybe it's chosen to take that first edge of weight 2, and that doesn't constitute a full solution. And so we can't really say what its value is. We can't say whether it's optimal. What does it mean to be optimal so far? Locally, we've made the optimal choices, but that doesn't mean there are long-term consequences about what you've done, right? So somehow we want to say, after the algorithm has made some decisions, it hasn't gone wrong. And what does that mean? That means even though it's made these irrevocable decisions, it's still possible that it will return the optimal solution. So we could say the optimal solution, what? Well, it's consistent with, it extends the choices. A sub t is the choices made by the algorithm so far. Right, this seems like a good loop invariant, but for example, if the algorithm chose the lion and the optimal solution contains the lion, then we haven't gone wrong. That seemed like it was a good thing to do. But the problem is there may be many, many optimal solutions, some of which contain the lion and some of them don't. And so we have to change this loop invariant, and let's change it to saying there's at least one optimal solution that's consistent with what the algorithm has done so far. So I like to draw this picture where let this be the set of all optimal solutions. There are many of them, and the ones that are on fire are the ones that are not consistent with what the algorithm's done so far, right? So they're still optimal solutions consistent with what the algorithm has done so far. And then when the algorithm commits to takes the next object and commits to it or rejects it, some of these possible solutions are no longer possible. And so I'm kind of saying, well, these are bridges that are burnt, right? And it's okay to burn some of your bridges as long as you don't burn all of them, as long as there's at least one optimal solution still consistent with what the algorithm has done.